Let's see. Okay, so I hope you can see my screen with the laser pointer and everything else. And throughout the slideshow, you can just please feel free to interrupt me at any point and ask questions if you need to. So what we'll do is we'll have 30 minutes of this PowerPoint, this slideshow, and then we'll have 10 minutes of demonstration. And then it's back to you where you do the exercises of the course, but I'll get back to that. So in this first session of the course, so the first of 4 sessions, well, I'll give an introduction to the Classify Design tool and a course overview. And the specific content in this slideshow is we'll talk a bit about what is classification actually. So what is feature selection? What are decision trees? What are decision boundaries? What is random forest? Our flagship algorithm, so to speak. We'll also talk briefly about KNN, which is another algorithm we offer. And finally, about decision rules. And then after the slideshow, as mentioned, I'll give a demonstration of basic navigation in CDT. And after that, you will do these 4 exercises. So exercise 0 is just setting up the personal workspace for the course. So if you already downloaded all the files and put them in your workspace, you are done with exercise 0. But then we'll do exercises on here where we create a maze classifier from scratch based on standard color features. Second exercise is an overview of binary features, and I'll get back to what that means. And then we have exercise 3 with pet food kibbles. So just a few exercises to get you started. So you might already have encountered the blob tool, and it could be that you ask yourself, so what can the Classify Design tool, so what can CDT actually be used for? And it's used to create advanced classification models, and you can also use more advanced tools such as feature evaluation. So in blob tool, you cannot evaluate how good your features are for the problem, but you can do that in CDT. So the main differences between CDT and blob tool is that you can create a customized classification tree in CDT, and you cannot do that in blob tool. Yes, it's also easier to navigate and explore your data in CDT. And as already mentioned, you're able to make more advanced modeling in CDT, in contrast to the blob tool where you just you give the features, you press a button to generate the model automatically, and that's it. But in CDT, you have more control. And here we give a general overview of the course. So in session one, as we do today, we'll have basic navigation. And in 1 week, we'll do color features and transformations. In 2 weeks from now, we'll do shape, texture, and contour features. And finally, for 3 weeks from now, we'll do session 4, where we'll delve into some more advanced functionality that didn't make sense to put in session 1 through 3. And each session will include a short presentation, followed by sometimes a demonstration, and then followed by exercises under supervision. And exercises that are not finished during the session, you can do after the course or between sessions. And the way you can find the CDT manual is you can go to Wikimedia Lab, Help, User Manuals, Software, and CDT. So which kind of features exist in the software? And in general, we have 5 major, what we call feature providers. We have the binary features, so those include area, width, length, or the ratio of the width and length. We also have color features. So those are based on color spaces, such as the CLAP color space, and I'll get back to that in session 2. We also have the MSI features, so multispectral imaging features. We have the shape features that are based on, for example, compactness, convexity. So compactness is how circular an object is. So the more circular it is, the more close to 1 it will be. And again, we'll get back to this in session 3. We also have contour features where we measure the curvature or the bumps of a blob. So it could be that some of them are quite smooth on the edges. It could be that they are also quite bumpy or have some kind of curvature, and we can measure that with these features. Let me just check. Okay. And for texture features, we have so if there's a hole somewhere or some kind of gradient, we can measure that as well. For example, one well-known application is for insect hole detection, and you can use insect hole features to detect those. So now moving on to the important topic of classification. So we can ask, so what is even, what are we even trying to produce here? We're trying to make a classifier, and a classifier is an algorithm which simply takes in an input, so a selection of features, and then outputs a label, a class. And we sketch down the situation at the very bottom here, where you have some image data. So here you have 3 maize kernels, 3 wheat kernels, and 3 OSR kernels. And we chose some relevant features, so compactness, skewness, pointness, and so on. And we use that to train a classifier, which makes the decision whether it's maize, wheat, or OSR. And so as written here as well, the classifier learns to distinguish classes based on manually selected features, so features that we ourselves choose. And what is even a feature? So a feature is some kind of measurable property or characteristic of a phenomenon. So again, could be area, could be color, could be width, could be how rough the surface is, or any kind of, if there's a hole in there or something like that, something measurable, something that we can measure with the instrument. And the CDT tool has a large selection of these handcrafted features available. So moving a step ahead. So here we sketch out the situation again. So you have the 3 first steps as you saw before, where you have some labeled input data. You select features, you train a classifier. And what's new here is now we present the model, the classifier, with new unlabeled data. And it produces a prediction. And as you see here on the right, it produces 3 predictions, 2 correct predictions, 1 correct for the OSR, 1 correct for the wheat. But for the broken wheat kernel, in this case, it predicted this broken wheat kernel as wheat, which is incorrect. And there could be many answers for how this happened. This is a very common occurrence, not specifically for wheat, but in general for machine learning. And in this case, it could be that the input data didn't account for broken maize. So it's kind of up for grabs what happens when we present it with broken maize in the future, because broken maize was not included in the training data. It could be that also that the features were not sufficient. So that could be 2 reasons why we made this error here. So the way we can improve the model from now on is that we actually include broken maize in the training set, and these errors should not occur. So moving on to feature selection. So the modeler selects features that capture the characteristics of the data. And most importantly, you have to choose the features that are actually able to make the model distinguish between the classes. So in this case, we sketched out the compactness plotted against the area for these seeds. So you see that the OSR, they are quite small in terms of area, and they have a high compactness, which again, compactness is how circular an object is. So the more circular it is, the closer it is to 1 for compactness. And you see the compactness is quite low for the wheat and maize kernels because they are more elongated, they're more elliptical compared to circular. But in contrast to OSR, they have a high area, and we see that they are situated in these clusters here. So they are well separated, which makes compactness and area good features because they separate OSR, wheat, and maize quite well. So the way you could now establish a simple decision tree is by asking a series of questions. So in this case, you could ask, is the area below 40 millimeters? If no, if the answer is no, then we say maize. If the answer is yes, then we move on and ask a new question. In this case, is the compactness below 0.5? If no, it becomes OSR. If it is below 0.5, then it's wheat. So this is a very simple decision tree, and this is the building block of a random forest models. So, and we'll get back to that. But again, here, so you ask a series of questions, and based on the answers to those questions, you will label each individual. You will put a label. Also, here we touch on the subject of decision boundaries. And decision boundaries are simply the boundaries between these regions. So each region here, so if you make a new measurement, let's say you measure C that has an area of 35 millimeters squared and 0.0565 compactness, it will fall within the OSR region. It could be that it's an error, that it's not wheat or OSR, and we'll get back to this, how you remedy this situation. But at least for now, any measurement you make which falls within this region will be OSR. Any measurement you make which falls within this region will be wheat, and so on for maize as well. So moving on to what random forest is. So the most used algorithm here at Vitometer. So the random forest algorithm is simply a collection of multiple decision trees. So in general, we have 100 trees. So each tree sees a different portion of the training data. So we train 100 trees. Each of them see a different portion of the training data. And then the way the algorithm works is by majority voting. So each tree gives a vote. One says wheat, another says maize, and then we count up the votes. And the majority vote is the one that produces the final result. So you might have 100 trees, of which 80 say wheat, 19 say maize, and 1 says OSR. Then the 81 that said wheat win the vote, and that's the final prediction. And the reason why we use random forest compared to just a single decision tree is because it's more sophisticated, and it's often more suitable for complex classification problems. A second algorithm which we offer, but it's not so much used anymore, is the KNN. And the reason why we have it in the software is for legacy versions, for legacy purposes. So in general, I would choose to use random forest over KNN, but we also offer this one, and it's even more simpler to explain. So KNN stands for K nearest neighbors, and the procedure is you choose K, so the number of neighbors, and then prediction is made or decided by the K nearest neighbors. If you look on the left here, so you have the training data here. So you have two classes which are red and blue. And if you go out and make a new measurement, let's say you made the measurement -4, -1, then we find the closest in the training data. In this case, the closest data point is this blue point, and therefore the prediction will be blue. the blue class, because we find the nearest neighbor. And the background colors here just show what the nearest neighbor is. On the right, if we choose 5 nearest neighbors, you see the previously blue region will now be red, because the 5 closest neighbors, most of them are red. And also up here for this region, you see the 5 closest neighbors in most cases are blue. Okay, so moving on to decision rules. So CDT has 2 types of decision rules. One is called logical decision rule, where we have manually defined this decision boundary using logical expressions, and the statistical decision rule, which is an automatic definition of decision boundaries. So first I'll explain the logical decision rule. So consider the case again where we have 2 classes, let's call it X and O. And we show the decision boundary as this blue line. So here on the left, we have 2 classes. Again, we plot 2 features against each other in this scatter plot. And we have defined this decision boundary as determined by if feature 1 is above 50, or feature 1 is above 25, and feature 2 is above 20. If this statement is true, it'll be class 0, so it'll be X. If it's false, then it's class 1. So this rule is exactly so if a point falls above the decision boundary, the statement is true. If it falls below, the statement is false. So on the other hand, if you use a statistical decision rule, you get a more non-linear looking decision boundary like this. And again, if a prediction falls above the decision boundary, it will be class X. If it falls below, it's class this O. And here, the decision boundary is determined by voting between the decision trees in the random forest. So there's also 3 different types of files in CDT, and it's quite useful to explain from the beginning what they actually mean. So we have the classification model, so a CMDL file. We have a classifier, which is an point VMCLF file, and a blob collection file. So the blob collection file has all the blobs, has all the classes, all the features. On the other hand, the classifier doesn't have any of the blobs. It has the classification tree, the train tree, the classes and the features, but it doesn't have the blobs. And the classification model has all of these, so it has both the blob collection and the classifier. And in this slide, we summarize this information. So again, a blob collection contains a set of blob images, and these blobs can have feature sets and classes coupled to them. A classifier is the file with the classification tree, but no blobs. And the classification tree is saved when it is fully trained and without the training blobs. And this file is the one you actually take and put into a recipe and use, for example, on the autofeeder. And finally, the classification tree is the file with both the tree and the blob collection. So it has all of this. And so therefore, a complete model is a combined version of both the blob collection and the classifier files. And one important piece of information is, so when we go to the file menu, as in most other programs, you can use the open tool or open menu item to open blob collections, classification models, and classifiers. And when you use the option save as, you save your model locally on your computer. And when you want to create a classifier, you would use the create classifier menu item. And then you can use the export function. So let's say you only want to work locally and you only want to save your model locally. You would then only use save as. But if you want to share the model with us or any of your colleagues on another machine, then it would use the export as functionality. And that is what we summarize here in this text. So again, save as is where you save the model locally on the computer. Create classifier is where you take the classification model and save the classifier. And export is where you want to, if you want to take the CMDL and put it on another location on the computer or move it to a different machine. Okay. Let's see. So here we give an overview of the binary features. And the binary features, they measure basic information about a blob, such as the area, the length, the width, in millimeters or pixels. It could also be the ratio of the width and area, or the ratio of the width and length, or the average or maximum distance to the closest edge. And some examples are included here. So area, average edge distance, diameter area, length, width, and so on. For example, so here you have some examples of different blobs. You see some of them might be quite long compared to the others. For example, this OSR seed, if you measure the ratio of the width to the length, I believe it will be quite close to 1 because it's very symmetrical. Where the length is almost the same as the width. But for the other seeds, you see that they are quite more longer than they are wide and so on. So you can use these features to differentiate between these different blobs. And for this last slide of the slideshow, we sketch out how the CDT software looks. So if you start on the left, you see here we have the blob viewer, where you have different blobs, and each of them will have some reference classes and some predicted class. So at the very top of a blob, you have a reference class, and then below you have the predicted class. And we also have here at the bottom, we have the image viewer and the feature viewer. So if you select a blob, let's say for instance this wheat kernel, you can look more closely at this blob, and you can also see the specific feature values. Here in the top center, we have the classification tree. So here you have the actual model which someone has implemented. And in the very first node, this unknown node, the model makes the decision whether it's inert material, other seeds, or cereals. So if we were only living in BlobTool, this is how far we could get. We could only predict inert material, other seeds, and cereals. However, since we are in CDT, we can take a step further. And at this node, other seeds and cereals, we can make further decisions. So let's say that you predicted a blob as other seeds. You can then use this node to predict it further as other unknown foreign, maize, sunflower, and so on. Same as if, let's say, a seed was predicted as cereal, we can make a second decision whether it's wheat, rye, oat, or barley, and so on. Down at the center bottom here, we also have a scatter plot of features for, again, compactness and area. So here you can see the distribution of all the blobs for compactness and area. And at the top right, you see all the classes, the labels defined in this problem. So here you can choose their name, you can choose their color, you can choose their statistical factors. And finally, here at the bottom right, you have all the selected features of the problem. Okay. And that concludes this slideshow. Let's see, so just gonna check the chat. No questions. Okay, so if there's no more questions, then we'll go ahead with the demo. Okay. All right. So if you want to follow along in CDT, you can do that. So we have this file called basic navigation demo. So you can, if you want to, you can open a classification model and access the CDT course workspace, and it should be in there. But if you don't want to follow along and you just want to see what I do, you can do that as well, because you will do this exercise as the first exercise as well. So let me just adjust this. So let's say you open a new blob collection like this, and you see the blobs. Maybe the OSR and the wheat kernels, they are nice and they look like this. But the the maize kernels, they appear to have been cut in quarters, something like this. But that's actually not the fact. It's just the way that the blob viewer shows them, represents them. So what you can do as the first thing, you can go to Tools, Options, and you can adjust what we call the core width and the core height. In this case, we can change the width to 300 and the height to 300. And you see on the left here that now the sizes, the dimensions have changed. Let's see. So you can also zoom in and out of the blob viewer. So if you hold the space bar and zoom in and out, you can change the representation. And you can also, again, select the different blobs. So if I want to select all the maize, I can select the ones at the top here by holding the left mouse button and dragging. I can also hold Control and then left click on the blobs here. Like any other software. I can also press Control A, then I can select all of them. And one more useful shortcut is Control I. So let's say I selected all the maize and then I press Control I. It will now select all of the selections I had not selected before. And if I press Control I again, it will select the maize from before. So something like this. Let's see. Okay, so we can also create new classes. These. So on the right, you can right click and select new. And let's call this one maize. And this one wheat. And finally OSR. Or maybe I went a bit too fast. So you get this view up here where you can choose the name, you can choose the color. So you can choose various colors here. And you can choose the statistical factor. We'll go back to that, what that means. And now you see it on the right, on the left here, you might have cases where the blobs have disappeared because you perform one operation or the other, but you can always go to the unknown node. You can right click and show blobs in node, and then they will reappear. So now that we have created classes, we can assign classes to each blob. So if I select all the maize kernels, I can right click and add reference class, so maize. And if I use the Control I shortcut, I select all of the ones that are not maize. I could then right click and view selection. And now you see I'll only be observing the OSR and the wheat kernels. So if I select the wheat kernels and then Control I to select the OSR, and then finally I can label the OSR kernels. And then I could choose to go back to the unknown node, right click and show blobs in node. And now you'll see if you put your mouse over the reference class here, you'll see it says reference classes maize. What else? Okay, so the next thing is then how to actually create nodes in your tree. So now you only have this unknown node. And we have to tell the model which nodes the model should have. So if you right click on new children, you'll get this box up and you'll choose Maze, Weed, OSR. And now we have created this configuration. Let's see. So now the next step is to create a model is to actually choose features. And down here in the Applied Features window, you can right-click and add feature. And then you get the Apply Feature window will appear here. And I always like to go in and click a provider. So then it will order the various features according to each provider. So here now you see that we have the 8 binary features, and this block here is all the color features, and we'll go back to these in the session 2. But I'm just showing some of the features here for overview. And then we have the contour features and the shape features, and finally the texture features. So for this example, we can choose compactness and area. So you see now area and compactness, they appear down here in the lower left right-hand corner. And now, quite importantly, we need to select a node. So you left-click on the unknown node here, and then we would select the features and right-click on them, and then calculate features on blobs and node. And now when you click on any blob, this one, for example, you'll see down here in the left-hand corner, the area and compactness of this specific blob will be shown. So you could press each individual one to note down the value, but it's easier to look at a scatter plot. So what you can do is you can go to View, Feature Statistics, and then choose Scatter Plot. And you'll get this plot up where you can choose Weed, OSR, and so on. And you can choose area as feature 1 and compactness as feature 2. And here you will get the plot of the distribution of compactness against area. Let's see what else. Okay, so there's also another useful feature, software feature in the blob viewer where you can, if you right click, you can sort by either the reference class or predicted class, but also by a feature. So if you want to sort by area in descending fashion, so from lowest to highest, now you see you have sorted all the blobs. So the largest ones in terms of area at the top, and the smaller ones at the bottom, or at the top, I mean. Let's see. Okay. So you can also choose to right click on the image viewer here and choose properties. And here you'll get the specific, you can say properties for a blob. So here you can have all the wavelengths of this specific maze blob, and you can see the strobe times used and the specific wavelengths. You can also get the width and height dimensions, the pixel size as well, so how many millimeters there are per pixel. And finally, you can also right-click and open blob in Meter Lab. So here I will open blob in Meter Lab, and you can now do more analysis of this blob if you want to. Okay, that actually concludes the demonstration. So if there's no more questions, we can move straight on to exercises. There's a question in the chat? Okay. Oh. I have a question regarding statistical factor. What is the use of changing it? Okay, so statistical factor, let me just go back. It's actually beyond the scope of this session, but the use of it is so I can share a document with you made by Carsten. So he invented a method where you have a lot of seeds. You measure the mass of the seeds, and then you get the mass density. And from those numbers, you can get the statistical factor. And this allows you then to get a weight estimation when you use the autofeeder. So does that answer the question? I'll just share my screen again so I can show you the exercises. So all of you should have this document here. So you downloaded 2 folders. So the course material folder, where you can find these documents, and the other folder which is the workspace, which you have to copy into your personal workspaces. This is the CDT course workspace. And in this document here, you have the exercises for session 1. And basically exercise 0 is where you actually have copied the CDT course folder into your personal workspaces. So if you already did this, you're done with exercise 0, and then you can move on to exercise 1. So we always recommend that one of you share your screen so we can help you. So if you have any questions, just tell me, and you can share your screen, and when we can get through whatever the problem is. All right, I'll stop sharing. You?
Yeah, Kristen, I mean to say that when we have the blob details saved, can we have a Excel and in which all the feature and its values, numerical values are transferred to it? Like for example, size, shape, and color details. When we are running the samples, we need to save that. At present, it is not doing that.
Okay, yeah, I think that's something we are working on.
Oh, okay.
I'm gonna write it down, and I'll get back to you when we have that in the software.
Okay, any approximate time period? Because our current customer is in need of that, and we've already installed 1 unit over there.
Okay, I think maybe a few weeks, a month, something like that. Maybe less.
A month. Okay. Yeah. Thank you.
No problem. This is beyond the scope of the course, and maybe we should look at this in a follow-up meeting, Tara. Because this is a segmentation issue I can see. I'm gonna note it down so we can have a follow-up support meeting. Hello, Bharat.
Hi, how are you?
I'm doing well, thank you. How about you?
I'm always fine. Whatever it is out of the scope, apart from this meeting.
Sorry, the sound is quite low.
Okay, whatever it is out of the scope, apart from this meeting, you may please take it up in the next session, and otherwise you can respond back separately.
Yes, I was thinking we could have a follow-up meeting for the soybean foreign matter.
Okay. So when can we have that also you schedule? Because we people are also having a lot of sales meeting and traveling. So if you can make it up sometime in the next week beginning, we'll appreciate more.
My calendar is free Friday or next week, Monday, Tuesday, Wednesday, something like that.
So this Friday is tomorrow?
Yes.
Okay, you can take up, no issue.
I have time after 1 p.m. Danish local time. Let's see, what is that in Indian?
What time do you want in the Indian time? Let me know, so accordingly I can make up.
Okay, I can do after 17:30 Hyderabad time on Friday.
Hyderabad time?
Yes.
This is the same time of ours in Baroda.
Okay, great.
Same time.
So,
okay.
So 17:30, I have time after that on Friday, but I can do earlier on Monday or Tuesday, Wednesday next week.
No, this is okay to us.
Okay,
Friday.
I'll send you a Teams invite.
If you
Sorry?
would make it up 1 hour early, would have been more better. Instead of 17, if you can put it up on the 16:30 is a fine.
But I only have time 17:30 onwards. Before that, I don't have time.
Accept it. Done. Go ahead.
So, okay. So you want me to put a Teams meeting for 17:30?
Yep.
Or
17:30 is fine with us.
Okay.
Tomorrow. All right.
I'll send the Teams invite.
Okay. Anything else, Shweta?
Okay, I sent the invitation on Teams for you. So you, Bharat, and Shweta, let me know if I should include anyone else.
My team will be there. My team also will be there. No issue.
Sorry?
My technical people also will be there in the session, so we'll manage that part. No issue. Myself, Shweta, and my team.
Okay.
We all will be there.
Okay.
Right.
Let me know if I should add anyone else for the email.
No, we will share the link here itself. No issue for that. Right.
Okay, that sounds good.
Thank you once again. Thank you very much for today's session. And really, it was informative, and whatever the things are remaining, we'll conclude by tomorrow.
Yes, of course. No problem.
All right.
कल उसको rice वाला भी पूछ लेना. Soybean and rice both.
Yeah. We have some things, Shweta, which will take over for the soybean and rice and everything tomorrow.
Yes.
Okay.
Okay, that sounds good. Yeah.
Right. Anything else, Shweta?
No, not at present.
Okay, so we can leave the meeting.
Okay.
I'm having another meeting in the next 15 minutes.
Okay.
Right. Thank you once again, Christian.
Thank you,
care of
Bharat.
your health. Take care of your
Yeah,
health.
thank you.
Right.
Thank you very much. Bye-bye. Hello, Damien. What's up? Do you see my screen? Let's say you only want to calculate for these wheat kernels. Then you can right click and say calculate features on selected blobs. But if you want to calculate on all of them, then you can choose unknown node. And then you say calculate features on blobs in node. That's the difference between the two. Also, if you now deselect, so if I click anywhere here, I have deselected the node. Now you will not be able to calculate features on blobs in node. Does that answer the question, or? Okay. It's because so in this case, it's a very simple model, and it could be that you make maybe it could be that you make, let's say, OSR broken. Let me just make an example here, OSR whole. Maybe let's say after you have classified OSR, maybe you want to make a second node called OSR broken and OSR whole. So now it makes sense to be able to calculate on different nodes. For example, the top node might use some features that are not used in the node down here. It makes more sense when you get blobs, let's say when you have 100,000 blobs, and maybe you don't want to calculate all features on all the blobs to save time. Did that answer the question? Okay, yeah, let's do that. Thank you.
Daniel, we use that feature to take a overview at the screen only. Otherwise, we have to save individual blobs and then check it in a Excel file. So I think that answer you are looking for, why we keep it on the screen and why it is required to check it on the screen. So you can read some features, values over screen over there on left-hand side. And then you can decide through over the blobs, like these are the features which is different from each other, and then you can use it. Otherwise, you have to go to the Excel and check all the readings and compare all the blobs, what is a plus and what is a minus. I think that would be the answer, maybe.